This video by Naobi production. It is a very nice video. Thanks to Naobi production for giving such a nice video. Thanks to Naobi. Now I'm going to discuss chemical ionization. That is another kind of ionization, that is chemical ionization. In chemical ionization, the ionization of the analyte is achieved by interaction of its molecule with ions of reagent gas such as methane, tertiary isobutane, ammonia, nitrous oxide, oxygen, and hydrogen. Here you see this is the ions. Here you see this is the sample, the analyte. When the analyte reach here, so here you see the reagent gas such as methane or ammonia is interact here with the analyte, and the analyte here in this diagram here you see when it interact with the reagent gas, so it convert into what? It's converting into ions, and the ions are attracted toward the analyzer. Chemical ionization, again here you see here again the reagent gas, and it's the reagent gas interact with the analyte, and it's chemical ionization is lower energy process than electron ionization. Ions are produced by collision of the sample with ions of the reagent gas that are present in the ion source. Sample ions are produced by the ion molecule reaction of reagent gas ions and sample molecule. Some common reagent gases such as methane, ammonia, and isobutane are used in chemical ionization. Positive chemical ionization, and there will be negative chemical ionization. Both possibilities are over there. Advantages: used for high molecular weight compounds, used for samples which undergo rapid fragmentation in EI. Limitation: not suitable for thermally unstable and non-volatile sample. Relatively less sensitive than EI ionization source. Sample must be diluted with large excess of reagent gas to prevent primary interaction between the electron and sample molecule. Field ionization. Field ionization is used to produce ion from volatile compound that do not give molecular ion by electron ionization. It produces molecular ion with little or no fragmentation. Application of very strong electric field induce emission of electron. Sample molecules in vapor phase is brought between two closely spaced electrodes in the presence of high electric field, that is from 107 to 108 volts per centimeter. It experiences electrostatic force. If the metal surface is properly geometry, a sharp tip or cluster of tips are thin wire and is under vacuum 10 to 6 torque, this force is sufficient to remove electron from the sample molecule without imparting much excess energy. The electric field is produced by applying high voltage 20 kilovolt to specially formed emitters. In order to achieve high potential gradient necessary to effect ionization, the anode is activated by growing carbon microneedles or vesicles. As the concentration of sample molecules is high at the anode, ion molecules reaction often occurs, which result in the formation of protonated species MH+. Thus both M+ ion and MH+ ion are observed in field ionization spectrum. Here you see this is the vesicle. Here you see this is the analyte. When it reach here, so it going to the electron are ejected, and when the electron are ejected, it's converted to M ion or M+ ion, and here this is accelerated, it's moving toward the analyzer. Advantages: as fragmentation is less, abundance of molecular ions is enhanced, and hence this method is useful for relative molecular mass and empirical formula determination. Disadvantage: not suitable for thermally unstable and non-volatile sample. Sensitivity is less than ion source. No structure information is produced as very little fragmentation occurs. The very important part of mass spectrometer, that is mass analyzer. With the adventure of different types of ionization source that can vaporize and ionize molecules, it has become necessary to improve mass analyzer performance with respect to speed, accuracy, and resolution. More specifically, quadruple ion trap, time of light reflection, and ion cyclotron resonance mass analyzer have undergone numerous modification improvement over the past decade in order to be interfaced with MALDI and ESI. The first mass analyzer made in early 1900 used magnetic field to separate ion according to their radius of curvature through the magnetic field. Types of mass analyzer: continuous analyzer, pulse mass analyzer. Continuous mass analyzer, these analyzers are similar to a filter or monochromator used for optical spectroscopy. They transmit a single selected mass to charge to the detector, and the mass spectrum is obtained by scanning the analyzer, so the different mass to charge ratio ions are detected. They include quadruple, filter, and magnetic sector. Pulse mass analyzer, these are the other major class of mass analyzer. These are less common, but they have some distinct advantages. These instruments collect an entire mass spectrum from a single pulse of ions. This results in a signal to noise advantage similar to Fourier transform or multi-channel spectroscopic technique. Pulse analyzer include time of flight, ion cyclotron resonance, quadruple ion trap mass spectrometer. Quadruple mass analyzer, here you see quadruple rods, there are 4 rods, and here you see quadruple mass analyzer is one type of mass analyzer used in mass spectrometry. A typical quadruple mass analyzer consists of 4 rods with a hyperbolic cross section that are accurately positioned parallel in a radical array. The quadruple rods are typically constructed using molybdenum alloy because of their inherent inertness and lack of activity. Very high degree of accuracy and precision in rod machining and relative positioning are required to achieve unit of mass. Here you see it consists of 4 rods. 2 rods are positively charged and 2 rods are negatively charged. Here you see this is the source slit, and here this is the detector, and here resonant ion detected quadruple rods. Quadruple mass analyzer benefits: classical mass spectra, good repeatability, relatively small and cost-effective system, low energy collision induced dissociation, spectra leads to efficient conversion of precursor to product. Limitation: limited resolution, peak height are variable as a function of mass discrimination. Peak height versus mass response should be tuned. Not compatible for pulse ionization methods. Low energy collision induced dissociation. Rely most probably on energy, collision gas, pressure, and alternative factors. Application: majority of bench-top GCMS and LCMS system, triple quadruple MS-MS system, sector quadruple hybrid MS-MS system. Magnetic sector mass analyzer. Here you see this is the magnetic sector mass analyzer. It consists of the magnetic source, high magnetic source, lighter atom, there is the heavier atom. Magnetic sector mass analyzers are the most mature of the mass analyzer technologies, having enjoyed widespread use from 1950 through 1980s. Magnetic sector bands the trajectory of ion accelerated from an ion source into the circular path for a fixed accelerating potential, typically set between 2 and 10 kilowatt. The radii of these paths are determined by the momentum mass to charge ratio of the ions. In such a manner, the ions of different mass to charge ratio are dispersed in space. So here you see that ion which having small mass to charge ratio, so it will be detected more, it will be bending more, and the R will be small, okay, and here the biggest mass to charge ratio, so there will be less force, and this less force will cause less bending, okay, and it will be positioned at different part of the detector. Benefits: classical mass spectra, very high reproducibility, high resolution, high sensitivity, high dynamic range. Limitation: not well suited for pulse ionization method, for example MALDI, usually larger and higher cost than other mass analyzer. Application: all organic MS analysis methods, accurate mass measurement, isotope ratio measurement, quantification we can do with the help of magnetic sector mass analyzer. Time of flight mass analyzer. A time of flight mass analyzer is a non-scanning mass analyzer that emits pulse of ions from the source. These ions are accelerated so that the heavy ions equal kinetic energy before entering a field-free drip region, also known as the flight tube. Here you see this is the flight tube. Time of flight instrument consists of a pulse of ion source, an accelerating grid, a field-free flight tube, and a detector. So what's happening? Here you see this is heavy ion and this is the light ion. And the time of flight when they are running from this point to this point, so the heavy ion will take more time and the light ion will take less time. And based on the time of flight difference, so the ions are separating from each other and they are reaching to the detector. Time of flight analyzer, different modes of time of flight analyzer. The mass analyzer used in time of flight can be either a linear flight tube, applying a geometry that the flight to reduce influence of neutral particles, or employ V-type or W-type, or there are different types of different modes of time of flight analyzer. Benefits: fastest MS analyzer, well suited for pulse ionization method. Limitation: requires pulse ionization methods or ion beam switching. Fast digitizer used in time of flight can have limited dynamic range, limited precursor ion selectivity for most MS experiment. Application: almost all MALDI system, very fast GC-MS system. Quadruple ion trap analyzer. The quadruple ion trap mass analyzer is a recently developed mass analyzer with some special capabilities. The quadruple ion trap is an extraordinary device that functions both as an ion store, in which gaseous ions can be stored for a period of time, and a mass spectrometer of a large mass range, variable mass resolution, and high sensitivity. As a storage device, the quadruple ion trap confines gaseous ions, which are either positively or negative charged, and when required, ions of each polarity also. A typical three-dimensional quadruple ion trap consists of a cylindrical ring electrode and two end-cap electrodes. End-cap electrodes contain holes for the introduction of ions from the external ion source and for the ejection of ions toward the external detector. HE bath gas, here the 1 millibar is used to stabilize the ion trajectory in the trap. Here you see this is the sample is over here, and here you see these are the trap. Here you see, so this is end cap electrode, here this is a ring electrode, this is the detector, here is the detector, and here when the ions are attracted to moving toward the detector, so we are getting the spectrum. Quadruple ion trap analyzer benefits: high sensitivity, compactness, and mechanical simplicity. Ion molecules reaction can be studied for mass selected ions. High resolution, non-destructive detection is available using Fourier transform techniques. Multi-stage mass spectrometry. Limitation: poor quantitation, very poor dynamic range, collision energy not well defined in collision-induced dissociation. Quality of the mass spectrum is influenced by many parameters such as excitation, trapping, and detection condition. Mass measured accuracy is relatively poor. Application: benchtop GC-MS, LC-MS, MS-MS system, target compound screening, ion chemistry, non-destructive ion detection. Fourier transform ion cyclotron resonance mass analyzer. Fourier transform ion cyclotron resonance mass analyzer is a type of mass analyzer for determining the mass to charge ratio of ion based on the cyclotron frequency of the ions in a fixed magnetic field. FTICR is the highest performance MS technique available, offering unrivaled resolution and mass accuracy. FTMS can be considered as ion trap system, where the ions are trapped in a magnetic rather than the quadruple electric field. The isocyclotron resonance mass spectrometer uses a superconducting magnet to trap ions in a small sample cell. This type of mass analyzer has extremely high mass resolution and is also useful for tandem mass spectrometry experiment. Here you see this is the trapping plates, here the magnetic field, and here you see the excitation core, and here you see the FID. This is the frequency spectrum, and this is the mass spectrum. Benefits: highest mass resolution. Limitation: dynamic range is limited. Application: ion chemistry, high resolution MALDI and electrospray experiment for high mass analyte, laser desorption for material and surface characterization. Detectors: once the ions are separated by mass analyzer, they can reach the ion detector, which generate a current signal from the incident ion. The most commonly used detector in MS are as follows: is Faraday cup, electron multiplier, photomultiplier diodes, charge or inductive detectors. Faraday cup involves an ion strike the diodes, barium oxide, gallium phosphorus or cesium's antimony surface, which causes secondary electron to be ejected. This temporary electron emission induces a positive charge on the detector and therefore a current of electron flowing toward the detector. This detector is not particularly sensitive, offering limited amplification of signal, yet it is tolerant of relatively high pressure. Here you see this when the ion strike this surface, so there is ejection of electron, and these electrons are attracted toward the diodes, and there is the amplification of current. Electron multiple tube. Here you see this is the electron multiple tube. Ions come, and here it consists of the diodes. There are different diodes. So here when the ions strike this diodes, so there is ejection of electron. This electron is further multiplied here. Another strike with another diodes, and here, and there is the amplification of the current. And the current is we are getting the signal, so it goes to the is a spectrum. Array detector. Here you see this is consists of many photomultiplier tube here. So there are many diodes here, and the whole spectrum we can take the whole spectrum of the sample. The array detector is a group of individual detectors aligned in an array format. This is the array format. The array detector, which specially detect ions according to their different mass to charge ratio, has difficulty to use a magnetic sector mass analyzer. Specially differentiated ions can be detected simultaneously by an array detector. The primary advantage of this approach is that over a small mass range, scanning is not necessary, and therefore sensitivity is improved. Charge or inductive detectors. Charge detectors simply recognize a moving charged particle or ions through the induction of a current ion the plate as the ion moves. This type of detection is widely used in FTMS to generate an image current of an ions. Detection is independent of ion size and therefore has been used on particles such as a whole virus. So here you see there is the charge detection, time of flight, and here you see this is the charge detection. And when the charge here reaching here, there is only a detection of the charge, and it doesn't depend on the particle size, but it depends on